welcome to 8th lecture of stability of structure. So, what we were discussing? We were discussing the effect of shear deformation on the critical load, right? We will demonstrate that how shear force and shear deformation basically helps basically reduces the critical load, and if it reduces the critical load, it lead you to non-conservative side, right? So, it must be accounted for in design. Okay. If we neglect this shear deformation, then it might lead to an unconservative design, right? Of course, shear deformation is significant, as you all know that it is significant when in beam cell plates and cell, when its span by depth is what? It depth is span by depth ratio basically is smaller, right? So, generally if it is less than less than 10, less than 8, then we consider the shear deformation to be significant. The way you have considered the shear deformation in beam, right? We have learned Euler Bernoulli bending a beam, right? Beam theory. But then if you include shear deformation, that where you give rise this to Timoshenko beam theory, right? Similarly in plate you have thin plate theory, right? What you are learning in plates and so. Now, if you consider this which is Kirchhoff plate theory, right, thin plate, where you neglect the shear deformation, the deformation is purely bending, you see. So, plane section remain plane after deformation, right, that is what is the assumption. But in thick plate you have to consider shear deformation, and that is why that assumption that plane section will remain plane is no more valid. You need to consider additional rotation of the cross section. So, that theory which includes the shear deformation is by Reisner and Mindlin theory. Okay. Similarly, in cell, thick cell, you will see the Nagdi theory, okay, for the thick cell, including shear deformation. So, here we will first demonstrate for the influence of critical, shear deformation on critical load. So, for that, once again we are adopting energy, method that is very intuitive and very easy, right. So, here is a we are considering a column, right, and is subjected to load. You see that here it is hinge, other end is also hinge, but it is allowed, the axial deformation is allowed, right. Okay. So, this way we can consider the shear deformation, strain energy of bending. Strain energy of bending is the contributed by bending moment as well as the shear, right. So, bending moment can also be expressed in terms of deformation, like integration E I d2 W dx in terms of curvature term, but we are next considering in terms of bending moment, right. And then the additional term is coming because of shear. This term basically is the additional term because of shear, which we neglected in earlier. Now, we include this thing and we will see that what is the influence. And for that, you see that for the shear force I am considering is Q. So, V square by 2 Ag, and then is nothing but the shear correction factor. Shear correction factor, it varies from 2 depending upon the geometry on the section, but 5 by 6 is typically used for this rectangular section, right. And then shear force is P dW dx, that from where this is coming, right, P dW dx, right. So, this is the contribution of the axial force in shear. So, now and then the bending moment can also be expressed as, for this case at least, as far as this thing is concerned, you see that this is out of plane deflection W as a function of x. So, I can write bending moment as P into W, right. This is the bending moment. Let us substitute it there. Okay. So, P square W dx by 2 EI plus integration 0 L n by 2 A G, and Q is nothing but P dW x square dx, right. This is the way it is, right. Now, we can simplify it further. So, that is not a problem. So, I just take this P square by 2 EI outside, integration 0 to L W square dx plus n P square by 2 A G integration 0 to L dW x square dx, right. Now, we assume this out of plane deflection. We can apply a procedure similar to Rayleigh. We assume some the displacement profile satisfying the essential boundary condition. That displacement boundary condition if it is simply supported this and this, and here the displacement is 0, here displacement is 0. So we can assume W is equal to maybe something like a sin pi x by L, and let us assume that only single mode is governing. Okay, let us find a single mode. Okay, so it's fundamental. We can have other terms also included, but I am considering a single approximation. Okay, single term approximation. So if you take and substitute, substituting and then you integrate integration w square dx and dw dx square. So here you will see that I am just expressing the u. Okay, I will just express the u, and you will see that final expression of u. You can integrate, right? It w square sin square pi x by L, right? And integration sin square pi x by L dx is nothing but L by 2. Similarly, double derivative, single derivative is cosine pi x by L, right? So I am just writing final expression. This is p square L divided by 4 ei plus it will be n p square s square pi, a is the amplitude, pi square divided by 4 a g L, right? It's fine. Now this is the strain energy of bending, right? Strain energy of bending. Now we equate this one with the work done, right? For the in order to find the critical load, we equate it with the work done. The work done that this axial force is doing, and it is going through out of plane deformation, right? So out of plane deformation is this point will move, right? This point will move, and what is that move? Delta. Delta you can integrate the Van Karman nonlinear strain, right? To get the in plane deformation due to out of plane displacement, right? So what was that? So I am removing this. So if we write W, nothing but P into delta, and this is P, and delta is nothing but you just integrate integration 0 to L W dx square dx, right? Okay, and then P equal to integration 0 to L dw dx square. So once again we assume Wx to be a sin pi x by L, right? Substitute it, and then you will see if you integrate, right, then you will get it P square pi square by 4L. Now for buckling, for critical load, right? For buckling, what we have seen that what happened energetically, that I am standing here, right? So during buckling, the whatever axial force is there is applied, that axial force is going to work on me, right? And then that will allow me to do out of plane deflection, right? The buckling is happening, right? So I mean instead of writing U and W, you can write delta U delta W. So I am just writing U to W, okay? And then if you equate these two terms and you simplify, that's where I am going to write the final. The expression will be P will be pi square Ag Ai L square Ag plus N pi square Ei. Okay, that's the expression, and then we will further simplify it. So if we further simplify it, then it is pi square Ei upon L square, then 1 plus N pi square Ei by A G L square, and pi square Ei by L square is what? This is nothing but P critical load. So this is P critical 1 plus N P critical by Ag. So what we see that here, the critical load here, maybe I am going to write this P is nothing but what? The critical load in presence of shear deformation, right? So, I can write that P critical, I can write here that P critical, in presence of shear deformation, it becomes P critical whatever is the pure bending divided by 1 plus, in P critical, that was for bending, and then A G. You see dimension, this is also a dimensionless quantity because P critical, P critical bending was nothing but pi square EI by L square, okay, critical load, okay. So, A into G is the same dimension as force, right, the unit is same, so it is a dimensions quantity, right. So, 1 plus some number. So, you see this denominator is always greater than 1, right. So, P critical we can clearly understand from here that P critical in presence of shear is less than P critical in presence of bending, right. So, shear deformation, the shear. So, shear deformation helps in reducing the, let us write down that what we have learned the lesson that shear helps me here reduces the critical load, and hence must be accounted for, and shear deformation is significant. Hence, shear deformation are significant to avoid unconservative design, non-conservative design. In fact, I mentioned to you there was a deep, there was a structural failure, and that was due to our lack of understanding of shear deformation. Okay. So, what we have learned that shear deformation reduces the critical load. In fact, in late 90s, I mean not late 90s, around 90s, when all this, or even before that, late 80s, lots of shear deformation theories were coming actually, okay, for plate and things, including this Jane Reddy's shear deformation theory. Now, what we are considering here, for most of the shear deformation theory, the first order shear deformation theory is by Timoshenko, right, in beam, and in plate is resonant binding, right. So, where we consider one additional rotation of this cross section, these are most thoroughly discussed in finite element or mechanics class, in your mechanics class, okay, and theory of plates and cell. But you see that the deformation, the shear force distribution is parabolic, right. So, there is an inconsistency. So, for that people introduce higher order shear deformation theory, that is beyond first order shear deformation theory, and that is where it gives rise to Jane Reddy's higher order shear deformation theory, Professor Kant's shear deformation theory, and all this theory is not asymptotically consistent. There are asymptotically consistent shear deformation theory by Babuskas. Okay. So, all this theory they demonstrated the influence, and it has been a very hot, very important, because very easy to, topics for PhD. Many PhDs has been guided on this. However, later people realize that it is not that significant for many cases. Unnecessarily you do not require to consider the shear deformation. Okay, if it is significant, then only. It was particularly significant because we were using laminated composite, right. In laminated composite, you have having a series of lamina, and they were glued together to form laminated composite, and because they have a low shear resistance, so there the shear deformation will be significant, and that is what all refined shear deformation theories are important. Okay, you see. So, even the higher order shear deformation theory, when you include for this here in buckling, so there have been lots of some studies there. Okay. So, shear deformation become important in L by D is less than 10 or maybe less than 8 or so. Okay. So, that means it is a deep beam, okay, deep beam, or deep cell, and then deep plate and things like that. Okay. So, now the shear, same things another way we can also find out, it is very simple. So, we have used energy method, but we can use other method. I will just briefly talk about it, So, I mean, if you consider that, consider a, cantilever, okay, and this fellow is deforming, right. So, here it is subjected to P, and then it is basically it is deforming, So, there is some deflection whatever, and now you see that what we write that, that the curvature d2w dx2 beam bending, right, dw dx2. So, it is bending moment by EI, first is m by EI, right, and by bending moment is what? Bending moment here in this case at least, if bending moment will be what? If this deflection is w, and assume that, from here this distance was nothing but delta, okay. So, then whatever is the, bending moment is nothing but P into, delta minus small w, right. This is the bending moment, right. So, this is the bending moment, but then in addition to that, so you see that this is the bending moment, but in addition to that, because of the shear, there will be additional curvature. So, what is the what is the shear? Shear, what is the shear deformation? Shear deformation is psi, I am assuming that this is shear deformation, and let us assume that first order shear deformation is valid, okay. Well, this shear deformation will be what? The shear deformation is nothing but V by Ag, and then N will be there, of course, N, right. V by Ag, because that is the, that is the additional rotation, right. V by Ag is the deformation. I am assuming that this is another rotation of that, the transverse normal, right. And then this V, we have learned that this V is nothing but that V N by Ag, this V is nothing but P dw dx, that is what we have, we know how this P dw dx is coming, right. So, now this is the, bending curvature, right, this is the bending contribution, bending curvature, and if this is the shear deformation, that is rotation. So, shear curvature will be what? Shear curvature will be what? D psi by what? Dx. The shear curvature, that will be nothing but what? N P Ag. This is shear curvature, right? This is shear curvature. So, let us also bring it there. This is shear curvature. This is the curvature due to shear curvature. Once again, we are assuming that, first order deformation is valid, and that is why in order to enforce the consistency between shear stress distribution and shear strain distribution, we are putting the N, that is the shear correction factor, right. So, all of you understand, or you are looking like a, vacant look, you should not have that. You understand what I am talking about, right? Okay, good. So, now I am removing this part, So, okay, P is equal to delta minus W, I am going to put. So, P delta minus W by EI plus NP by Ag d2W dx2. So, I will take this out here. So, here what I will write 1 minus Np by Ag d2W dx2 is equal to P delta W by EI. Now, you see that this one, or I mean, you can, this equation you can solve. I mean, you just you take this thing and you also take this thing. So, first of course, this is the homogeneous part, inhomogeneous part. I am not solving, but you can solve it, right. And if you solve it, then you will see that one of the eigenvalues that you are going to get, you will see that. So, you will see that here the way I will just take it here. So, here I will just write d2W dx2 is equal to P by EI by 1 minus NP by AG. Okay. So, this is basically the term which will be eigenvalue. Okay, I know. So, I am going to write. So, if you just enforce the boundary condition, maybe for this he fixed and hinge, you should write that x is equal to 0, w is equal to 0 and dw dx is equal to 0, right, something like that. Then you will see if you solve it, then you will enforcing this. I am not doing it, but you can see that P by EI 1 minus NP by AG, this is a y square by 4L square. 4L square, why it is coming? Because you see that because the effective length is 2L, right? Okay, so now you see. So what you are going to get here, P, this P is nothing but this P is nothing but here you just write y square EI y 4L square, and you just if you multiply it, it will be 1 minus NP by G, and then if I take it the bottom by polynomial expansion, it will be approximately NP. Do you see the same expression? So, same expression we are getting. So, P critical load in presence of shear is nothing but this is nothing but P critical presence of bending 1 plus NP by AG. Do you see that? 1 plus NP and this NP in critical in bending. Okay. The same expression we are getting. So, both way energy using energy approach as well as by energy equilibrium approach, writing the governing differential equation considering the the curvature contributed by shear deformation, we are arriving on the same expression. So, you see that in presence of shear deformation the critical load reduces, right. So, it is a consistent. Okay. Now, what we are going to do, I am going to do the so all of you understood, right. So, the effect of shear deformation on buckling. So, shear deformation reduces the critical load, okay, reduces the critical load. Now, we are going to consider the large deformation of column. Okay. So, we are going to consider once again and I am considering that it is going through large deformation. Okay. And I am just here I am x axis I am going to consider here and y axis I am going to consider here, okay, and then this angle is alpha, and then here I am going to consider there is this arc, there is another curvature which I am denoting as S is along this arch, okay, xy arch, and then this is the origin, and so P, and then this deflection, of course this deflection, this one is basically W. Okay. Now, what we are going to do is that bending moment, we can write as bending moment is nothing but P into W. That's what we can write, P into W, right. So, the P is axial force, then whatever is the lateral deflection, P into W is the bending moment, right, for this, and W is a function of x or function of s, whatever, right. Now, we can write it, that this is nothing but minus EI, see, EI d2W dx2, but we cannot write d2W dx2 because we are considering finite deformation of column. So, instead of d2W dx2, we can write d theta by ds, we can write, right, d theta by ds. That means we are distinguished, see, in small deformation theory, in finally small deformation theory, x is same as s, right, but in this case x is not same as the is. Yes, you understand? Or I am going to write S. S is the basically curvature, S is the arc length coordinate, S. You understand what I am trying to say, right? This is for small deformation, right? And here what we are considering the finite deformation, right? Finite deformation. Large deformation, finite or large deformation rather, large deformation. So we cannot write x as same as s. You understand what I? So whatever we were writing w into writing as a function of x, I mean we can write as a function of s, right? You can write as a function of x as well. There will be some mapping between x and s. So when I am writing, so EI d2w dx2, so EI is the flexural stiffness and d2w dx2 is the curvature. Curvature is nothing but change of slope, change in slope. So change in slope, that means if I consider this slope is theta, at theta, basically at s is equal to 0, we are writing, theta is equal to alpha, right? That is one of the boundary conditions, right? So I am considering, we are distinguishing between the x and s coordinate, is the deformed. So change in slope is nothing but d theta ds, right? d theta ds. Let us write this small s, okay? Okay. Okay, so d theta ds, you understand this is perfect, right? So then this one is nothing but p into w, right? So now what we will do from here, we'll d theta by ds plus e by ei w is equal to 0. That is the governing equation, right? Isn't it? Let us do one thing and you will understand what I am going to do. So we'll differentiate it 1 second. So d theta ds2 plus e by ei dw ds, okay, is equal to 0 if you differentiate it 1 second, right? So you see that here now what we are going to do, see, if I consider the small segment here, like it is deforming, right? So this is ds and then this is the so this is ds, this is ds and this is dw, right? Dw, and this angle is theta. So dw ds is nothing what? This is nothing but sine theta, right? Sine theta. So I can write this is d2 theta ds2 plus I will write p by ei. Let us define p by ei as lambda square. Okay, the way earlier we used. So lambda square, and I am just going to write sine theta is equal to 0. Okay. Okay. Then I will do further simplification. So what I will do, d2 theta ds2, and then I am going to write d theta ds into ds plus lambda square sine theta d theta is equal to 0. So see, d theta ds is nothing but I am just this is nothing but d theta I am multiplying both sides, right? Fine. Why I am doing that? Because that will lead to some simplification of the equation. Okay, and please note that lambda is the parameter, lambda square is nothing but p. So lambda is nothing but root p by ei, p by EI, okay. EI is the flexural stiffness, P is the axial force. So, until this you follow how I am coming here. Nowhere I have highlighted the small, highlighted the large deflection assumption, right. There is no assumption of small deformation. This is a large deformation theory of beam, okay, and this of column, beam column, okay, and that's why this is called this. You know, when we consider large deformation of a column, this is called Elastica. It's a little fancy name, Elastica, okay. Elastica. Elastica. There is a band, right? This band, Elastica, huh? So you see that, don't get confused. So this Elastica is nothing but this fellow, huh? This deformed, because it's elastically, we are still assuming that it's a large deformation, but the material is good enough that it is not going to, it is still remain elastic. So the non-linearity is only coming from the geometry, not in material. You understand that? Okay, Elastica. Okay, good. So now so what I will do now here, I will integrate it. I will integrate it for theta. Okay, so what first what I am going to get d theta ds square half minus lambda square cos theta is equal to maybe some constant, see, constant of integration. Is that fine? Integration sin theta d theta is nothing but minus cos theta, right? Huh? And is that fine? Because d theta ds square, if you differentiate it twice, 2 d theta ds, you see that 2 d theta ds, and then d2 theta ds 2, okay, d2 theta ds 2. So 2 will cancel out. Is it fine? By on integrating, right? C is the integration constant, right? Integration constant. Constant, huh? Okay. Now you see that we have to find out this constant, we have to enforce the boundary condition, right? So what the boundary condition we are going to write? Enforcing boundary condition. So boundary condition is at what we have seen, that at s is equal to 0, theta is equal to alpha, and not only theta is equal to alpha, at s is equal to 0, that means at this point I am considering this the origin, at s is equal to 0. Bending moment is also 0, right? So what is bending moment? Bending moment is nothing but d theta ds is equal to 0. So that means here d theta ds is 0. Why? Because it's a bending moment is 0. Here you write bending moment 0. Bending moment is 0, right? So if that is, then enforce this condition here. So if you enforce this condition, then let's write. So d theta ds is equal to 0 minus lambda square cos alpha is equal to c, and then c is nothing but minus lambda square cosine of alpha, okay, fine. So now I am just removing this equation, you please concentrate on that, okay. So what we obtain ultimately, that half d theta is square minus lambda square cosine of theta is equal to c is minus lambda square cosine of alpha, and then half d theta ds square is equal to lambda square cosine of minus sine of alpha, and then I am going to write, you know, d theta ds square is equal to 2 lambda square cos theta cosine of alpha. Okay, now until, so please note that. So you see here that which sign to take, plus or minus, you see that with increasing s, this is the positive direction, right? With increasing s, theta reduces, right? Isn't it? With increasing s, theta reduces, that means this must be negative, right? Why it is so? Because, you know, the bending moment is and curvature are opposite, that's what minus sign is coming, right. So with increasing theta, you know, with increasing s, sorry, with increasing s, you know, theta reduces, huh? And so, you know, let us take negative sign. Negative sign is valid. Negative sign. Let us take, so d theta ds I am going to write minus lambda root 2 root cosine of theta minus cosine of alpha, right? Okay. And here if you do little simplification, minus lambda root 2, so cosine of theta is 1 minus 2 sine square theta by 2, and this is minus 1 plus 2 sine square alpha by 2. Okay, this will cancel out. Minus root 12 का take out, so 2 lambda root sine square alpha by 2 minus sine square theta by 2. Okay, that is what we obtain, right? So to write it further, minus you see what I am doing. So from here ds I am doing like that, right? Now I am going to integrate. What I am going to integrate? I am going to integrate from here to here. It is symmetric, right? From here to here. Why? From here when s is equal to 0, and from here L by 2, right? So integration 0. S is L by 2 is nothing but arc length, right? You know, length of the right, isn't it? So this length is going to be, you know, deformed in the form of an arc, right? So L by 2 is fine. And then here theta is 0, and here, sorry, here theta is nothing but alpha, right? This angle is alpha, that's what. But here theta is 0 because the slope is, you know, 0, right? So is that fine, right? So now that I can write here, so here it is L by 2. L by 2 is equal to, here I am going to do, so minus, so here I can write 0 to alpha, right? So negative sign I can take out, d theta divided 2 lambda root sine square alpha by 2 minus sine square theta by 2. You see that? Or I can cancel out these two, so I will write lambda L. This I will take lambda L is nothing but integration 0 to alpha d theta divided by root sine square alpha by 2 minus sine square theta by 2, right? Now I will simplify this integral. This integral, what I will do, I think somewhere, you know, since this expression I am missing half and half, that I missed somewhere, okay. alpha 0, that is perfectly fine because alpha, so from here I am taking alpha and here it is basically 0, right? So that's what it must be 0 to L, so L by 2, okay, thing and then 2 will come. Okay, that's fine. So I will now change this integral. You see that this integral will be simplified to a, you know, will be simplified. So how we can simplify this integral? This integral will lead to elliptical integral. So how? So we will assume that this peak sin alpha by 2 will put as p cap. There is a parameter p cap, okay, or you can write p also. That's not a problem. P or the or no, write p. P is a parameter, okay, and that sin theta by 2 we will write as p cap sin phi. Now, so that means what essentially we are doing from alpha theta this, we are basically transforming this as p and phi, p cap and phi. Why so? Because you will see that if you do see substitution, it will lead to a standard integral. Okay. So if we do, then what will happen? So sin theta by 2, p cap is nothing but sin alpha by 2, and this is sin phi, and then you see that here I am differentiating cos theta by 2 d theta 2 is equal to sin alpha by 2 cos phi d phi, right? So here cos phi is nothing but root 1 minus sin square theta by 2 d theta by 2 is equal to sin alpha by 2 cos phi d phi, right? Or let's see that root 1 minus sin square theta by 2, sin square theta by 2 is p cap square sin square phi, okay, p cap square sin square phi, right? And this is d theta, this is 2 sin alpha by 2 is p cap, you see that, and this is cos phi d phi, okay. So from here you see that from here I can from here, please see here there is no space coming here, please see. So that means d phi d theta is nothing but d theta is nothing but 2 p cap cos phi d phi divided by root 1 minus p cap square, sin square phi. Clear? So do you see that from alpha theta how we are going to p cap and phi? Now these two parameters have some meaning that I will tell you later, okay. That means here what I am going to do, it will give you very beautiful structure of the integral. So I am removing everything, I will only do lambda L, this I am going to, you see that this is lambda L is nothing but integration, and now so alpha, you see that 0 to alpha, right? So theta is 0 to alpha, okay, and then we are going to make it phi. So when theta is theta is 0, what is phi? So if theta is 0, you see that theta is 0, what is phi? If theta is 0, what is phi? 0, right? Is 0, right? But if theta is alpha, so theta is alpha, this alpha. So sin phi is nothing but 1, so phi is pi by 2. So pi by 2, right? So from here, this integral, I am going to write here, so 0 to alpha. So 0 to alpha, instead of here I am going to 0 to pi by 2, right? And d theta is nothing but, what is d theta? D theta is nothing but this one, 2 p cap cos phi d phi 1 minus p cap square sin square phi, right? And what about this one? In the denominator, whatever is there, what is that? Sin square alpha by 2 minus sin square theta by 2 is sin square alpha by 2 means p cap square minus sin theta by 2 is nothing but what? Sin theta by 2 is nothing but p cap sin square phi. So p cap cos phi, right? So in the denominator, I am just 1 by p cap cos phi. Is that fine? All of you please note that. I am transforming the integral. So d theta, the differential, I have expressed in terms of phi and p cap and phi, right? And then the denominator root sin square alpha by 2 minus sin square theta by 2, I am simplifying as p cap cos phi. Clear? All of you please note it down. Huh? All of you understood? Right? Noted it down? Okay. So now I have obtained this one. I am removing all other things, right? You have noted it down. Okay. Good. This integral, I mean, some of you may recall, what is this integral? This form of integral, is this integral familiar to you? Anyone? No? This integral is nothing but the elliptical integral of I think first or second kind, okay? Elliptical integral of, I think this is second kind, okay? So see, when I am converting alpha and theta to p cap, this is a standard integral. Why they are called elliptical integral? Because this integral were developed, I think, mid of 17th or let's say century by Euler and another fellow Galileo something, okay? Not that astronomical this one, okay? Euler and one of his co-worker. So they were trying to find out the arc length of an ellipse, arc length, and that's what they have find this integral. This integral appears to find out arc length of an ellipse, and then this p cap and phi. P cap is nothing but this parameter. P cap is called eccentricity. P cap is used to describe eccentricity, and phi is called modular angle. Modular angle is angle subtended at the center of the ellipse. Okay, not I mean there are so modular angle and eccentricity. So this integral, elliptical integral of the second first kind, elliptical integral of the first kind can be used to describe this. What is lambda? Lambda is root phi by L, right? So now from here we will see what we can do. Okay. So elliptical integral are available as a built-in function in all these mathematical software, be it MATLAB, Mathematica. If you give elliptical integral is generally defined here, you see that this is defined as 2 and this is defined as elliptical k cap, p cap and phi. So k cap is defined as the elliptical function. So this elliptical function you can give the command for given p cap and phi, given value of this eccentricity and phi modular angle, you can find out the value, and if you find out the value, you will be able to find out lambda L, right? So for and p cap depend on alpha. So this alpha is this rotation. This alpha basically define designate that how much deformation it has, right? And it can have finite deformation, right? We will try to simplify it little bit. So what we are going to do? So all of you, what I will do? I will just simplify this. Okay. what I will do is that here this lambda L, let it be lambda L is equal to, I will just do like this 2 integration 0 to pi by 2. I will take this on the denominator 1 minus p cap square, sine square phi, minus half d phi, and then it is 2 integration 0 to pi by 2. So 1 plus half p cap square, right? Sine square phi plus half minus 1 by factorial 2, and then you will see that is I think 3 by 4. Okay, that will be 3 by 4. Let me write it down. Okay, 3 by 8, 3 by 8 cap to the power 4 sine 4 plus dot, dot. Okay, so we expand it using binomial, knowing the fact that sine phi is less than 1 and p cap is also less than 1. So this is a small number when appearing square term, so we can expand it using this expression. Okay, for the time being I am just keeping it, but then so then you can just do this term by term, you can integrate it, right? Not a problem. So when you integrate this to first, what will pi by 2 integration d phi 0 to pi, right, pi plus then p cap square by 2 integration 0 to pi by 2 sine square phi d phi, sine square phi d phi. You will see that here it will be another half will be there. Okay, half, then it will be plus just this can be simplified as pi 1 plus half. If you do this integration, you will see this p square plus 3 upon 8 square p cap 4 plus, and then I'll talk about this later. Okay, for the time being, leave it, and then from here I am just writing it lambda L is equal to, here I will just write pi plus y you see that is the expansion ultimately we are getting. Okay, and please note that p cap is equal to, p cap is sine alpha by 2. Okay, this is please keep in mind, and please keep in mind that lambda is nothing but p by ei. So what do you see here, that for, please note that for lambda L less than pi, lambda L less than pi, for lambda L less than pi, only theta is equal to 0 is possible, right? Is possible. That means the fundamental path, the column will remain at its fundamental path, right? Is possible. That means column remains at its fundamental path, theta is equal to 0. But as soon as lambda L is greater than pi, but lambda L greater than pi, theta not 0 is a path, right? That means, right? So there is a bifurcation occurring at theta. So what we lambda L less than pi, fundamental path is possible. But when lambda L greater than 0, theta is not 0 is possible. That means there must be a bifurcation at theta. So that means there must be a bifurcation. There must be a bifurcation there must be a bifurcation at what? At lambda L is equal to pi. So lambda L is equal to pi, there must be a bifurcation. You understand why we are justifying that? Because lambda L less than pi, no non-trivial solution is possible, right? But when lambda is greater than pi, there is a solution at theta is equal to non-zero value. So lambda L is equal to pi must be a point of bifurcation. What does it mean? Lambda is equal to pi, that means which is nothing but what? Lambda square L square is equal to pi square, and P is nothing but pi square EI by L square. That means that indicates the critical load, So bifurcation is happening at the critical load. The column is buckling. Understand? Bifurcation. So from the solution of the finite deformation Elastica, we see that a bifurcation is imminent at lambda L is equal to pi, and from there we also see the critical load which is leading to this bifurcation, pi square EI by L square. That's value we know. We all know the column which is hinged at both ends, right? The critical load is this, and that is indicating the bifurcation. Now, why did you consider the finite deformation of the, why do you consider elastic and not the infinitely small deforming column? Because now we can really gain insight what happened beyond critical load. So in order to do that, what we can do here, please note that all of you have noted down all these things, right? So what will happen, you see that. So but for P greater than PCR, that means for alpha is reasonably higher value, right? It's a little okay. So what is happened that, so lambda L, let us take a first term approximation, okay. So the first term approximation, so then I can write lambda L is equal to pi plus pi, and then 1 by 4 p cap square, another term I am neglecting, knowing the fact that p is a small. So what? Because p cap is nothing but what? Sine alpha by 2, and I am assuming that maybe alpha is not at 30 degree, okay. I am assuming alpha is maybe little higher. So when this assumption that sine theta is equal to theta is valid, when theta is less than is equal to 4 degree around. So I am just approximating is with alpha by 2, okay. So still, so then what we can write, lambda L is equal to pi plus pi and 1 by 4, and p cap is so this is of course alpha square by 4, right? You see that? So that means here what we can write, this is pi 1 plus alpha square by 16, right? Okay? And I will just remove all these things. So I can see that lambda L is being pi and then 1 plus alpha square by 16, and I will just write lambda square L square is equal to pi square 1 plus alpha square by 16 square, and then I will this pi square 1 plus, I will not take the square, I will take this alpha square by 8, and here it is p square is p by ei, L square is equal to pi square 1 plus alpha square by 8, and p is nothing but pi square ei upon L square and 1 plus alpha square by 8. That means I can write P by P critical is nothing but 1 plus alpha square upon 8. What does it mean? P by P critical means, so with this P by P critical, that means, with varying alpha, varying alpha, P, see, P by P critical, it is 1 is the 1 is buckling. There is very slight increase here, okay, and this curve is 1 plus alpha square by 8. very slight increase, very slight. What it remains to you? Symmetric stable bifurcation, symmetric stable bifurcation, but very little rising. So, you will see that if alpha, consider alpha 30 degree, if alpha is 30 degree, then P by P shear become 1.03. That means only 3% increase, only 3% increase in the load increase. See, theta is equal to 30 degree is a huge deformation. You understand, theta is equal to 30 degree, that means there is a huge rotation of the end, but even at that only there is only 3% increase in the load. Post critical rising path will only rise at 3 degree. So, it is a very it's definitely it is stable bifurcation, right, but very little post critical reserve, very little post critical reserve, okay, very little post critical reserve, post critical reserve, say only 3%. So, now to understand the post critical, so column does not show much post critical reserve. So, what is the takeaway from this? Column does not show. This is possibly supported, but any of does not much post critical reserve, post critical reserve strength, I mean reserved load, whatever it can carry. So, as soon as column reach the critical load, it almost depletes its load carrying capacity. So, we cannot rely the post critical rise for the design purpose, understand that, but we can clear. So, what kind of imperfection sensitivity will show? Stable post critical bifurcation, stable post critical 2/3 power, right. It will be imperfection, mild imperfection sensitive, 2/3 power law, okay. And then in fact not imperfection, it will be imperfection insensitive, because stable post critical path shows what? This is with increasing load, that is why there is a rise in post critical load, right. So, the critical load will enhance with increasing alpha. So, it will be 2/3 power law, but imperfection insensitive. Do you see a real example of those toy system what we have demonstrated? These are, we have demonstrated this whole essential behavior by taking rigid model with in spring, right. But do you see how those kind of qualitative behavior is exactly represented by real structure column? Do you see? So, that lies the beauty, there lies the beauty, okay. Now, for the Elastica, I will all noted down these things, right. One more thing two more thing I am going to show to you. So, one thing is that we have seen that K cap, P cap, alpha is P cap and phi, okay, that is integration 0 to pi by 2 d phi, that is the integral elliptical integral of first kind, 1 minus P cap square sin square phi, right. So, you can from here you can directly find out the, and that was nothing but lambda L. So, from different, and you must recall that P cap is nothing but sin alpha by 2 alpha and and phi and then and then phi phi we have decided, right, what was the phi. So, sin phi is nothing but P cap sin theta by 2, something like that, right. So, you can from there you can find out that, okay, any critical load, okay. Now, another small thing I am going to mention here, that. So, the way this elastica will deform is something like this. You see that here, if you take simplify, like it is P, and then here it will be maybe 4 degree, then it will be, it will be something like, this degree, this, you see that? This is the for different alpha you will see. So, this is some angle, this will be some angle. See that how alpha is increasing, alpha, and with this formulation, alpha is does not really change. Okay, this is the alpha. So, that's why this is called elastica. Okay. For different alpha, you can find out what is P, because lambda you can for different alpha you can convert that alpha to P cap and phi. You can find out the elliptical integral, this one, and from there you can find out what is P, right, and how much it is different from PCR. Clear? Okay. Now, if somebody asks you what is the deflection, what is the deflection? This delta I. What is the deflection of the tip, delta I? And also somebody might ask you not only deflection, but what is this? What is this? This is XA. This one, this one or this one, For that I am writing it. Okay. Now, for W it is easy, because what we have seen dW ds is nothing but what? Sin theta, right. So, dW is nothing but sin theta ds, and what is ds? What is ds? We have noted that ds is nothing but, we have noted that ds d theta is nothing but minus 1 by 2 lambda sin square alpha by 2 minus sin square theta by 2, right. So, this is sin theta, and ds is, it is minus d theta divided by 2 lambda root sin square alpha by 2 minus sin square theta by 2. Now, you can integrate it. W is nothing but, just integrate it. Integrate, how will you integrate it? Alpha to 0, right. So, alpha to 0, minus sin theta d theta divided by 2 lambda root sin square alpha by 2 minus sin square theta by 2, and here it, then you just write 0 to alpha sin theta d theta to lambda root sin square alpha by 2 minus sin square theta by 2, and you will see that if you simplify it, ultimately it will lead to a very simple expression. You will see that here you will be, once again you just substitute that you make everything in terms of P cap and phi. So, from alpha theta you do a variable substitution. From alpha theta you just go to P cap and phi. Okay. Then you can also convert it into elliptical standard integral. You will ultimately you will see that it will be something like this. I am just taking it like this here. I am taking it like this. Yeah. Please note it. Please note it. So, ultimately W will be from this integral. Ultimately, it will be 2 P cap by lambda integration 0 to pi by 2 sin phi d phi, and then if you do, then you will see 2 P cap by lambda. So, from here you can calculate what is the deflection, because P cap, this is very simple expression, right. W is equal to, so very simple expression. So, W is equal to 2 P cap upon lambda, So, for any alpha you can calculate P cap, and lambda is nothing but root pi So, for any P, level of P, you can find out lateral deflection W. Okay? Clear? You see that? Now, XA, similarly, you can also find what is XA. So, this is lateral deflection. Now, if you consider what will be the axial deformation, XA will be, I am just writing without XA will be, without deriving it, I am writing 2 by lambda integration 0 to pi by 2. Please note that this is integral of the first second kind, 1 minus p cap square sin square phi minus phi d phi minus L. Okay. So, this is the so elliptical integral of second kind, this one. So, here how this minus L is coming, please note that what we are doing, we are essentially integrating the arc length and then multiplying it to. So, that arc length, basically see this length total L is nothing but it is basically mapped into that arc, right. So, if we L is straight one. So, if whatever is this this mapping, now you take the projection of that. Okay, so, see this thing was mapped into like this. So, from this one, the projection of this curve, this one is given by this first term, okay, and you just subtract L from that. So, that is what you are going to get XA. Understand how we are getting? Okay. So, this and this is nothing but elliptical of integral of the first kind. Okay. Elliptical integral of first kind, of second kind. This is elliptical integral of the second kind. Okay. This elliptical integral, once again this parameter is p cap and phi. Phi is modular angle and p cap is eccentricity and L is the length initial. Okay. So, how to find out the what is the level of critical load that it, what is the level of axial force that it can carry for a given level of alpha deformation, right, that Elastica can carry, you can find out that. Then next you can find out the lateral deflection W as a function of alpha. Also you can also find out the compression in the deformation in the along the axis direction. Okay, fine. If you do not consider the Elastica, see you can see infinite small deformation, we do not care. There W is essentially 0 tending to 0, XA was tending to 0, alpha was less than 4 degree, here alpha can go to 30, 60, 90, 120, 150, 180, and even it can go to something like this, you see that, that is why it is Elastica. Clear? Okay, thank you very much for your class today. Thanks.